In the two-body system, the next thing that we'd like to start with is the single pulley systems. So the single pulley systems, we're going to be discussing Atwood's pulley and the Fletcher's trolley. So with pulleys, all a pulley is going to do is change the direction of the force. It's not going to change the magnitude or any of those things. It's just going to change its direction. For all the pulley things, we're going to assume a few things. We're going to assume the pulley's mass doesn't contribute to the system, and we're going to assume there's no friction between like the rope and the pulley itself. We're going to assume there's no friction between the axle and the pulley itself. We're going to assume that the rope used in the pulley has negligible mass and thickness, which is already one of our assumptions. And we're going to assume that the rope does not stretch, nor does it break. So this is going to allow us to assume that the tension throughout the rope is constant. This is really important. So first up, we're going to look at the Atwood's pulley. So the Atwood's pulley, you're going to have two masses that are unequal, really important. And you're just going to hang them over a pulley like this. So here's our pulley. We have the rope going around the pulley connected to the two masses. Now if the two masses were the same, acceleration would be 0. This wouldn't be an interesting case. But the difference in these two masses here, that is going to have different forces of gravity acting against each other. And this pulley is going to move in the direction of the greater force of gravity, or the direction of the heavier block. What we would like to do is we would like to derive an equation to get the acceleration for the Atwood's pulley, or the acceleration of the individual blocks. So in this derivation, I'm going to go kind of through the quick one, and then I'll show you a second one on a separate piece of paper of how we would deal with that. So we're going to have two masses, M1 and M2. I'm going to just assume M2 is bigger than M1. Doesn't actually matter. You could say M1 is bigger than M2. So the first thing that we want to deal with here is we want to begin with Newton's second law, or the acceleration is the net force divided by m. First thing is, when we're dealing with mass, we're actually dealing with the total mass of the system. So the system being our pulley, the total mass is going to be m1 plus m2. The net force, this one's a bit trickier. The net force, we want to think of it as what is driving this system to actually undergo the acceleration. So if I kind of look at my pulley up here, with mass 2 being bigger than mass 1, we're going to have a force of gravity because for mass 2, and we're also going to have a force of gravity due to mass 1. But with mass 2 being heavier, its force of gravity is going to be stronger than this force of gravity acting on mass 1. So because this force of gravity is stronger, this one is going to win out. This second mass is going to end up going down, whereas mass 1 is going to go up. We want to think of M1 as sort of like a counterbalance. This M2 is not going to hit the ground it's not going to accelerate at 9.81 meters per second squared. It's going to accelerate based on the difference between the two forces of gravity acting on the masses. So for us, we want to think of the net force being due to that difference in mass. So for us, we're going to say that F net, it's going to be that difference in mass times the acceleration due to gravity. And that's a really key point. We want that difference in mass to be what's driving the system. So what we can do, we can put this all together. We can say that the acceleration is equal to, here's my net force piece here. Here's my total mass piece down here. So we have this difference in mass times the acceleration due to gravity divided by the total mass. Or you may see it written like this. This A equals M2 minus M1 divided by M1 plus M2 multiplied by your acceleration due to gravity. So on a written response question, I'd expect you to kind of show a couple of steps of how you get that. So realistically, I'd expect you to kind of state something along the lines of, if I go back, stating that the mass is the total mass and the net force is this difference in mass times g. If you tell me those two things, I'd be very happy with that. On a multiple choice numerical response, if you want to show your work, doesn't really matter, you can go right straight to this. So that is one way this equation is derived. There's another equation, there's another way we can look at this. So I'm just going to kind of sketch this out on my little notepad here. What I'm going to do is I'm going to take the pulley and I'm going to just kind of deconstruct it. So here's my pulley here. And what I'm going to do is, instead of having the masses hanging, we're just going to stretch them out like this. So there's my second mass. There's my first mass. So what we have like this, we're just going to hold everything to the side, and we said M2 is heavier, so what that's going to tell me is that this is my direction of motion, which is what I'm going to call positive. Now, in this system, we can certainly look at all the forces acting in the system. On mass 2, we know there's that force of gravity pulling it this way. And on mass 1, we also know that there's a force of gravity trying to counteract that, pulling it this way. That's fine. Now, what some of you may want to throw in is you may want to throw in that force of tension. And if you want to do that, that's actually fine. We're going to ignore it, and I'll show you why. Tension's always going to act away from the object. So the force of tension on the block 2 here, it's going to act away. So we're going to have this force of tension acting away from the block. On mass 1, we're going to have this force of tension also acting away from the block. But you have to keep in mind the force of tension is constant throughout the system. What that means is that this Ft and this Ft here, they have the same magnitude. You'll also notice that they are pointing in opposite directions, or they're acting against one another. So Ft is going to cancel out. So when we're looking at the whole system, because of that force of tension, because the force of tension is kind of an internal force, we can actually ignore it entirely if we're looking at the whole system. So what we could say is that the net force on this thing, it's equal to this Fg2 plus Fg1, or then we got this M1g plus M2g. Now it almost looks similar, but you have to keep in mind for mass 1 here, since the acceleration is directed opposite to my positive convention, this g would actually have to go in as a negative. So we'd have something like this. M1g plus M2 minus g. So realistically, we're going to get something that looks like this. This should be M2, M1, M2, M1. My apologies. And then we get this M2g. And then instead of having the minus here, let's bring it out front. So we're going to get M1g. This is another way that we can get the net force for the Atwoods pulley. If you want to kind of deconstruct it, but you don't have to actually deconstruct it. You can just kind of say the net force is going to be driven by that difference of mass. How you want to approach it is up to you.